let's pick things up where we left them last week. And remember, we're covering chapter 5 in the textbook. So hopefully we'll finish the chapter today and start with a bit of chapter 6 as well, which is very related to chapter 5. So let's start by reviewing a little bit what we saw last week. We started by deriving error probabilities for these linear constellations. So we went through a lengthy derivation of the error probability, which recall has the interesting property that it's invariant to rotations and shifts in the constellations. That's a pretty important property. We saw that in general, for an arbitrary constellation, the error probability comes out in the form of a pretty nasty integral here at the bottom, which we cannot really solve in closed form. And so, I mean, in some cases we'll find expressions, but usually you run into this integral that you can't solve. So in order to get some more useful expressions, we went through this union bound expansion. And we came, after a little bit of work, to this expression for the error probability based on the union bound with this double summation. Okay. So it's a double summation of Q functions. So once again, we're finding these familiar Q functions that we already saw earlier in the course. Remember that in chapter 2, when we dealt with shadow fading, we also found Q functions because the shadow fading was log normal. So when we express things in dB, it was Gaussian in dB. And so we found Q functions. And here we have that the noise is Gaussian. And so when we express things in linear scale, we again run into Q functions everywhere. Okay. So this is the union bound expression. And then we found that there is a more compact and less tight expression, which is the simplified bound, which has, again, a Q function, but it doesn't involve this double summation. And it goes to, the simplification is based on the concept of this minimum distance, dmin, which is the minimum of all possible distances between every pair of points in the constellation. Okay, so easier to compute, but not so tight. And finally, we had this third expression, which is the nearest neighbor approximation, which in contrast with these other two is not necessarily a bound. So it doesn't tell us that there is an inequality. It's rather an approximation. So it could be below or above the actual value, but it tends to be very tight. And here we're using again dmin, and we're using a new notion, which is this mdmin, which is the number of neighbors at this minimum distance. So we derived these three expressions, and I think you've had a chance to exercise these during the homework. So by now you're probably hopefully familiar with the three of these, the three of them. The three expressions can be expressed in closed form for highest NR by using this approximation for the Q function in the form of an exponential. And you can always use this, but it's tight only for large arguments. So for largest NR is when it's really tight. But one can always use it as an lower bound. We went through this example. And by the way, one of you sent me an email correcting one of these numbers, and you were right. So this is a typo in the book, which I hadn't found, and I guess nobody had. So so the actual value here, if you have the slides that I had posted like 2 weeks ago, you'll see that you have a different number here, right? So I think you had here 3 point something times 10 to the minus 5, right? So there was the factor of 2 was not multiplied, and so I followed the textbook thinking it was right, and I guess one of you guys actually went through the computations, and so I appreciate that, and pointed out that actually the factor of 2 was not multiplied. So this is the correct value for the union bound. The loser bound is a little higher, as usual. It's less tight. And actually, this should be now 1.5 times loser, not 3 times. So some real-time editing. So keep this in mind, since in use slides it's still incorrect, probably. And finally, the nearest neighbor approximation gave us, and again, I corrected this number, I think, a value that is very close to the union bound. Okay? So we went through this example. which is now corrected. We noted here, and we'll be using this later today, that when there are only 2 points in the constellation, all these bounds are actually, first of all, identical, and second of all, they're exact. Okay. Now, we introduced the notion, so far we'll be talking about error probabilities, this P sub E, which is the probability that the symbol is in error. So the probability that the point that we declare in the constellation is not the point that was sent. So a point may involve more than one bit. In general, it involves. So there is a different notion, which is the notion of a bit error probability, which is the probability that the particular bit is in error. So we call this PB. And in order to get the possible PB given a certain PE, we can use a clever mapping of bits into symbols, into constellation. Remember, we talked about gray mapping, and we went through an example of how to do gray mapping. So we want to make sure that points that are neighboring in the constellation differ by only one bit, so that these type of errors, which are the most common, induce only one bit error. Okay, so that's gray mapping. And when you use gray mapping, under the approximation that all the errors occur between adjacent neighbors, we can approximate PE divided by K, which is the number of points in the constellation, which is log 2, I'm sorry, K is the number of bits, which is log 2 of M, where M is the number of points in the constellation. Okay? And then we started to introduce the three classes of constellations that are used in commercial systems. First one was PAM, which is here. But first, because let me cover this. We introduced PAM, PSK, and QAM. And we spent a couple of minutes here talking about synchronization. So remember, this is the structure of the transmitter and the receiver that we derived. And synchronization entails making sure that the oscillator here, the receiver, at frequency FC, has the same FC that is being used at the oscillator or the transmitter, right? If these are different, this frequency difference would integrate into a phase difference that would distort the information. So there is a special circuitry in the receiver that actually locks the frequency onto the one that is being used on the transmitter. So this is a very important task, and one that we're not going to have time to cover. So we'll be assuming throughout that this FC is exactly the same as this FC. Okay? So bear in mind that this takes a lot of work, but it is done with pretty high accuracy. So there is another degree of synchronization, which is in time. So we want to sample here every T sub S, every symbol time. So we want to make sure that the sampling points are aligned with the right points on the transmitter. So this requires time synchronization, which is also achieved with pretty high accuracy. And in the book, there's a section on this. If any of you is interested, you can read it out, but it is optional material. And finally, there is a phase here. You know, every oscillator has a phase. In this case, I'm calling it phi sub naught. And there's another one here. And we want to make sure if we're using anything that uses phase to carry information, like PSK or QAM, then these phases have to be equal. Otherwise, the information is going to be distorted by these phase changes. So for example, that would cause a rotation in the constellation. So we would be confusing one point with another if we have a phase difference. So these phases also have to be synchronized if we're using the phase to convey information. So for example, for PAM, we don't have to. But for PSK, we do have to. So we're going to be assuming that all the synchronization is done perfectly. And briefly, the three families of constellations, the first one is PAM, which remember uses only the in-phase component. So it lies on a line. So it's a bunch of points spaced by some common distance that we'll call 2D. So this spacing is common, so d mean is automatically 2D. And the decision regions are very trivial in this case, just by symmetry, right? You just draw vertical lines between every pair of points, and this gives you infinitely long strips, let's say, vertical ones. Each one is a decision region for a particular point, okay? And we can use gray mapping. Here it's exemplified with 4 points, but you can do the same thing with larger number of points. And remember that we only have one branch in the receiver and the transmitter because we don't use the quadrature component in this case. So that's what it looks like, the receiver. It's very simple. Then the second class of constellations was PSK. where the information is embedded in the phase as opposed to the amplitude. So what we have is a bunch of points around the circle with a common distance from the origin, and the information is in the phase of each of these points. So the decision regions here are just separated by radials that split every pair of points. And we can also use gray mapping. We saw here how to do it for 8 points. And the most general and common form of modulation is QAM, where we use both in phase and quadrature, both amplitude and phase. We use everything. So it's a bunch of points on the plane. And gray mappings are not always possible here. Sometimes they are, but not always. And the most common forms of QAM, or let's say a subclass of QAM, which is the most common, is square QAM, which amounts to independent PAMs on quadrature. So, for example, this would be an example. You have a PAM with 4 points on the in-phase axis, and another one on the quadrature axis. You multiply them out, and you get 16 points. Okay, so this has interesting properties because of this sort of symmetry, which we're going to be exploiting. We're going to be exploiting later today to derive some of its performance. So I believe this is where we stopped last week. So we'll take it from here. I just told you a couple of minutes ago that it's important to synchronize the phases of a receiver and the transmitter. Now, that is actually a pretty challenging task. So it takes a lot of complexity in the receiver to actually track the phase. So sometimes if we want to build a cheap receiver, we may want to do without the phase tracking, so without the coherence. So that actually can be done. There's a form of modulation called differential modulation that eliminates the need for phase recovery, although at the expense of some performance degradation. So in theory, one can use these differential techniques with both PSK and QAM, but it's very rare in QAM, so we're only going to talk about it in the context of PSK. Okay? So essentially, differential modulation is a form of modulation with memory. So rather than embedding the information in the phase of the signal, we're going to embed the information in the phase difference between successive symbols. Okay? So let's use a very simple example. The simplest form of PSK was the BPSK, which is the PSK with 2 points, binary PSK. So we have 2 points, 2 different phases, right? So BPSK would be, you have a point here and a point here, and that's it. The other points don't exist, right? You just have these 2 guys, phase 0 and phase pi. So in this case, the phase is in the information is in the phase itself. Now, in differential PSK, the information is in the phase differences. So we send a symbol with a certain phase, theta sub I, and then we send the next symbol has a phase which is theta sub I plus pi or plus 0, depending on whether we want to send a 0 or a 1. Okay? So the information now is in the difference between the phases of consecutive symbols. So the absolute phase doesn't mean anything, it's just the phase differences. So in this case, if we go from theta I to theta I plus pi, it means we send a 1. If we go from theta I to theta I, so the phase remains the same, then the difference is 0, so it means we send a 0. Okay? Now let's say we want to do the same thing with 4 points. So we want to have differential QPSK, right, which is called DQPSK. So we're going to have 4 phase transitions, 0, pi over 2, minus pi over 2, and pi. Okay, the 4 points in a circle, equally spaced. So in this case, if the kth symbol has phase theta I, then the next symbol will have one of 4 phases. Theta I plus pi over 2, theta I minus pi over 2, and theta I plus pi. Okay? So by these 4 different phase changes, we'll convey 0, 0, 0, 1, 1, 0, and 1, 1, the 4 possible combinations of 2 bits. Okay? And we could do the same. We could have 8 possible phase changes to send 3 bits, 16 phase changes to send 4 bits, and so on and so forth. Okay? So hopefully you get the hang of it. We can use gray mapping to map groups of bits onto phase differences, that we're doing here. I believe this is gray mapped. Right, it is gray mapped. And the receiver structure is very similar to the one for PSK, except for a one symbol memory. So you have in your textbook figure 520. So let me put it up. Okay, so as you can see, the first part is identical. We take the two branches. We have a cosine oscillator with a shift that gives us a minus sign. And we just multiply this out. We have the convolution with the G of capital T minus little t at the sampling. So this part is identical to the one for PSK. And here, instead of just sending these to the decision circuit, we have a delay of one symbol. All right. So we're going to compare the phases of one symbol with the previous one, which is so this is a storage memory unit that stores the symbol. So you can compare it with the symbol that comes right after. Okay. So a symbol is stored here in memory, and then the next one comes here, and these two are compared. So we can see the phase change between consecutive symbols and make a decision on that. Okay. So how do we do this comparison? Okay, so let's say that at time k minus 1, we send a symbol that looks like this. It has the amplitude A and phase theta of k minus 1, whatever that is. Okay, so this in low-pass notation, the received vector, the received signal is A times e to the j theta of k minus 1 plus some arbitrary phase, which is the one of the oscillator, which is irrelevant, plus noise, the noise at symbol k minus 1. And then in the next symbol time, in the next tick of the clock, we get r of k equal to the same amplitude, but a different phase, theta of k, the same oscillator phase, this one is constant, plus a different noise. Okay, so this is what we get at time k minus 1, this is what we get at time k. Now we want to compare the phase of these two guys to see the difference in phase, which is where the information is. So how do we compare the phase of two complex symbols like these ones? So it's actually very easy. All you do is you conjugate one of them and you multiply them out. Why? Well, conjugation, as you know, changes the sign of the phase. And when we multiply two exponentials, right, we add their exponents. So by doing this, we're subtracting the exponents, right? So we're subtracting what's on the exponent here, which is the phase. So we get something that has this theta of k minus theta of k minus 1, which is what we want to compute. All right? So using this very simple operation, conjugation of one of them and multiplication, we get this guy, which has the amplitude squared, because each one of them has the amplitude. And we have a phase term that has the difference. Notice that these two phi's cancel out. So the phase of the oscillator becomes irrelevant. It just cancels out. And we get the phase difference here of the thetas, which is where the information is. And then we get a bunch of other terms, right? We get this symbol times this noise, and we get this noise times this other symbol. So these are these two terms. And then we get the product of the two noises, one of them conjugated. Okay? So we have more noise than usual. We have a bunch of additional noise terms, which is the reason that the performance of these differential techniques are inferior than the ones that use the phase recovery. Okay, and we'll see later why exactly how to compute this. But essentially, we have three terms with noise here, and one term with the actual information. So when you put this together, actually, you're doing worse than you were doing when you had regular PSK. But you have the simplicity that you don't have to make sure that these, to recover the theta, make sure that this theta here is the same that you had at the transmitter. It just can be whatever you want. Okay, so that's it in differential PSK. We won't get much into it, but I want you guys to have a high-level notion. It used to be used in some systems, commercial systems in the 80s and early 90s, but all the new systems today use coherent detection, so they all track the phase. because the performance is superior. So this has been pretty much abandoned by now. It was done just for complexity reasons, but these days it's been pretty much abandoned. Any questions here? Doubts, confusion, concerns? None? Okay. Okay. A very quick notion, constellation shaping. Remember that when we talked about information theory in chapter 4, and that's something we just brushed over, but you may recall we said that to achieve capacity, the signals had to be Gaussian, right? Which is a mathematical idealization. But that result tells us that we should try to make our modulated signals look as Gaussian as possible. And a square QAM is quite far from looking Gaussian. So we can improve it by doing something called shaping. Okay. So, okay, let me draw a picture to help out here. Okay, so a Gaussian, a one-dimensional Gaussian looks like this, right? Now, we have a plane, we have a two-dimensional signal. So, a two-dimensional Gaussian, let's say these are the I and Q axes, okay? So it would look like a mountain on a plane, okay? Imagine a Gaussian mountain on a flat plane. That's a two-dimensional Gaussian, and bear with me because I'm not a very good drawer, but hopefully you get the idea. If you slice this in any direction, you get a Gaussian like that one, okay? So this is has symmetry with respect to this axis. So we can rotate this, and if you slice it in any way, you get a Gaussian. So, okay, so it's like a hill. So that's a two-dimensional Gaussian. So imagine now that this is the plane we look at from the top here, okay? So one of the properties of a Gaussian distribution like this is that it has this symmetry, right? So you turn it around, you turn it around with respect to this axis, central axis, and it's symmetric. It always moves the same, right? It's like spherical in this sense, right? So if you look at a square QAM, it doesn't have this property, right? If you take this is square, so if you rotate it 30 degrees, it looks different, right? It doesn't have this property that you can rotate it around and it remains the same. So to make it look more Gaussian, we have to make it look more circular, okay? So the way to do that is by using these cross QAM constellations, like this one, for example, which is not exactly spherical, but it's more round than the one we saw before, right? So we took some points and we moved them around. So I think here we have 32 points. This is a square 32. So it looks more circular than the one we had before. So by doing that, it actually has a superior performance. It's about 1 or 2 dB better than if you had the same number of points just on a square grid. Okay, so by reshaping them, you can make them a little better. And that's actually done. It's not done in wireless, because usually we have small constellations, but this is done in DSL, for example. So in DSL, they use huge constellations, very large. So I don't know if any of you guys uses DSL at home for high-speed internet access, but they use constellations with thousands of points. So the shaping becomes pretty important when you have thousands of points. Here you only have 32. So in wireless, no commercial system has more than 64 points. But in DSL, they use sometimes thousands. Okay, that's all I'm going to say about this. And this is the last topic of this chapter, which is pretty important, which is the pulse shaping. So we've been carrying around this pulse shape, G of t, throughout the whole chapter. And we haven't said much about it. So we've just been deferring it. So now we're going to tackle that. Okay? We'll talk about this G of t, which is the pulse shaping. So remember that all the signals have this G of t. So let's go back and look at one of them. Right? For example, QAM, right? We have the G of t here multiplying out both the in phase and the quadrature. Okay? So everything else are just coefficients and phases and stuff. So look at the baseband, right? Amplitude, phase. The only thing that has a temporal shape is g of t. So this determines what the pulse looks like over time. And the most trivial shape that comes to mind is a rectangular one. Okay, so pulse that looks like this. It starts at 0 or at some point in time. It has a constant value for duration t sub s, which is the symbol time, symbol duration, and then it just dies off very abruptly. Okay, that's probably the easy caricature of a symbol shape, and one can use that because it's very simple, but that's not what commercial systems use. So this is a very bad pulse shape. Now, why is it so bad? Well, okay, I already told you here, so it's no point in asking you. So the reason that this is bad is because it uses up a lot of bandwidth. Now, does any of you have an idea why this shape uses up a lot of bandwidth? If some of you have worked a lot with Fourier transformations before, maybe you can think about properties of the Fourier transformation. Yeah, that's a sin x over x function, exactly, which is a pretty wide function. The problem is that there's a discontinuity here, right? So there is a property of the Fourier transformation that tells you that for a signal to be compact in one domain, it has to be smooth in the other domain. So smooth means to have as possible to be being continuous. In fact, you can prove that if you have a temporal shape like this one, its Fourier transformation falls off in frequency with an exponential decay, so with frequency to some exponent, which is given by the number of derivatives that are continuous in the time domain. Okay? So here, how many derivatives of this function are continuous? None, right? Even the function itself is discontinuous, right? It has a jump here. So we want to avoid these type of jumps because this one gives you a sin x over x, which has these loops that go on forever. So being that bandwidth is so expensive, we want a signal that looks very compact and dies off very quickly in the frequency domain. So we have to smooth it out in the time domain to achieve that. Now, we have to respect some properties. Remember that G has to be unit energy and has to respect the orthogonality between the in-phase and quadrature. So remember that we had these conditions, right? We had that g square of t integrated times cosine square 2 pi f ct. This has to be equal to 1. And this had to be equal to 0, okay? And we can actually reformulate these conditions in low pass and just remove these cosines and sines. So we can just say that we want this equal to 1. Okay. So don't take my word for it, but this is equivalent. And this one is always satisfied. So we want to make sure that it's unit energy. And we want to make sure that we want to try to make it as compact as possible in the frequency domain, so it uses as little bandwidth as possible. And very important, we want to ensure that there is no intersymbol interference. Remember we talked about this before? We want to make sure that adjacent pulses don't interfere with each other. Okay? So for example, I just told you that we want to smooth out this rectangular shape, right? So imagine that instead of using a rectangle like this, we smooth it out and we say, okay, let's do something like this, right? Something like this, which is smooth, and it has the same area. We can make it so that it has the same area, so it has the same energy. This looks better, right? this will have a much nicer shape in the frequency domain because it's smooth. It has the same energy, so it seems to be okay. Now the problem is that after this pulse, there's another pulse that comes right after. So we have another guy here. So now the tail of this guy spills over this guy, and the tail of this guy spills over this guy. Actually, the tail may spill over several neighbors, right? So this could cause intersymbol interference if we're not careful. So we have to make sure in our design that also we don't introduce this interference, right? So it's pretty challenging. We have to meet all these conditions. But not to worry, it can be done.
If you just had but as long as the time period was the same as T of S, then that'd be fine, right? Because you wouldn't have that much.
As long as what?
As long as the period of your GT is equal to T of S.
Right, you're going in the right direction. So the question is, as long as the period of G of T is the same as T sub S, right? You're almost there. So now you'll see how to formalize this intuition into a mathematical condition. So it can be done, in fact, it can be done. And that's actually how you design these pulses. So we'll see it coming right up. So we want to avoid these tails here, which means we want to avoid that when we send the symbol here, right? And we sample here, we're also picking up the tail of another symbol that came before, or that's coming after. Okay, so that's what we want to avoid. And you just hinted at the way to do it, right? So we want to make sure that when we convolve G and, okay, so remember, we have this structure, right? We have G of T here, giving shape, and then we just go out in the air, coming to the receiver, and let's forget about the cosines here, because at the end they don't play a role. We're going to multiply by the other G here, which is just time shifted and displaced. So we have this guy and this guy involving G of T. Okay? So we have this convolution. And let's give it a name. Let's call P of T, let's use it to indicate the convolution of G of T with G of capital T minus T. Okay? So that's what we sample. So P is what comes into the sampling device here. So we want to make sure that these samples don't have ISI. Okay? So we want to make sure that P of T is 0 at the sampling instance of the other pulses, which is what you were saying essentially. Right? So
is G of T convolved with G of T aspects?
yeah, so the convolution happens here, right? So we send a signal that has shape G of T, and it comes in here, and it gets convolved with this other G, right? So then this is sampled, and you want to make sure that when you sample this guy, P of T, you pick up only one of the symbols. You don't pick up any of the neighbors. So mathematically, we can say, okay, let's sample P of T every T sub S. Okay, so we have P of T, and now we sample it, so we have P of KTS, where K is an integer, 0, 1, 2, 3, 4, 5, 200. And T of S is the symbol duration. So the sample version of P of T, we want it to be 0 everywhere except in one point. Okay, and at this point, let's say K equals 0, but it could be any other one. At any particular point, we will say it has a value which should be 1, but let's call it P sub naught to keep it general, but this should be 1 essentially. And everywhere else, in all the other sampling points, which are for other symbols, we want it to be 0. Okay? So this condition ensures that there will be no ISI. Now, it is convenient to transform this condition and move it to the frequency domain. So how do you do that? All right, so this is the answer, and I believe that in the textbook there is no derivation here, so I'll take you through it, just sketch how you go from here to here. Because essentially it boils down again to Fourier transformations. Okay, so first of all, how do we sample a signal? Okay, we have P of T, and we want to sample it every capital T sub S. How do we sample a signal? You guys not seen this before? Can you multiply by something, for example, to get a sample version? Exactly, impulses. So what we want to do is we want to multiply it out by a train of impulses spaced by T sub S. Very good. So we want to take P of T, and multiply it by an infinite train of pulses, delta of t minus t sub s, minus k t sub s, for on k. Okay, so k is an integer, going from minus infinity to plus infinity. So this is a train of impulses, spaced by unit amplitude impulses, spaced by t sub s. And by multiplying it by p of t, we just sample this p of t at these points. Everybody okay with this? Yeah, you multiply it out, so this gives you p of k ts, right? So everywhere else is everywhere else you just get 0. You just pick up these points times delta. Okay, but essentially these impulses are just picking up the value of the function at those points, and everywhere else you just get zeros. So you want these to be 0 everywhere except in one point. Now let's move these into the frequency domain. Okay. So what happens to multiplication when we go to the frequency domain? So let's say that the transformation, Fourier transformation of P of t is capital P of f. Okay. Convolution, exactly, right? Multiplication becomes a convolution with the Fourier transformation of this guy, right? So we have to form an infinite series of impulses. Okay, so you probably don't know what this is, but the Fourier transformation of a train of impulses is another train of impulses. It's actually pretty easy to prove. You can just use the definition of Fourier transformation and do the integral. And you get another series of symbols, another train of impulses, this time in frequency, and spaced by 1 over t sub s, which is the reciprocal. And there's a scaling factor outside of 1 over t sub s. Okay? So now we can bring this P of f inside the summation. And what's the convolution of a signal with an impulse? Anybody remembers? Come on, guys. This is basic Fourier transformations, right? When you convolve something with an impulse, what happens? Nobody? Okay, you just move out the signal on top of the impulse, right? So if the impulse is at 10, you move your signal up to 10, right? So it just shifts the signal and puts it on top of where the impulse was, right? So what you get is 1 over Ts summation of P of f minus K over Ts. Okay? So this is what you get. You get a sum of shifted copies of P of f. Okay? And now you're done because you want this to be equal to P sub 0. Okay? So you can just multiply both sides by capital T and you get this condition. Okay? So we transformed this sampling condition into this frequency domain condition. And this is called the Nyquist criterion because it was devised by Nyquist, the same guy of the Nyquist sampling theorem. Okay. So for order to be ISI free, the pulses P in the frequency domain, P of f, must satisfy this criterion. So luckily for us, there's a bunch of pulses that satisfy this condition. One is rectangular pulses. We know that they have no ISI, right? Because in the time domain, they do not open up, right? So if you use rectangles, right? We have this rectangle. We put another one here, another one here. These guys are non-overlapping, so there is no ISI. So necessarily, they meet this condition, and they do. There are cosine pulses, which are sometimes used in frequency modulation, but we're not going to deal with these guys. And then there are raised cosine pulses, which are the ones used by every single cell phone in the world. So this is what's used universally to shape signals, okay? Raised cosine pulses. They're a little more complicated, but they meet this condition. So they have no ISI. They're very compact in the frequency domain. And the unit energy, so they meet all the conditions, okay? So this is their shape in the frequency domain, and this is the shape in the time domain, okay? So in the frequency domain, they have three regions. Starting at frequency 0, they're flat up to a point, which is 1 minus beta over 2 t sub s. And beta is a parameter that we can adjust. It's called the runoff factor. So, for example, in GSM phones, the ones that you have, for example, most of you guys are singular users. So in your singular phones, this beta is 0.35. It's typically around between 0.25 and 0.35 in that range. It's called the runoff factor, and it's a controllable parameter, okay? So the frequency is flat from 0 up to a point. Then it rolls off gracefully with this shape over here. It's a fairly involved equation until it touches 0, and then it remains 0. So the best way to see this is in a picture. You have it in figure, let's see, 526 and 527. So let me take you there. Okay, 526, here it is, okay? So let's look at one of these guys. So there are different plots for different values of beta. So let's look at beta 0.5, okay? It's flat here up to this point, okay? Then it starts to fall off with this smooth shape. Then it touches 0, and then it remains at 0. And the same on the other side, okay? So if beta is equal to 0, it becomes a rectangle. So actually the rectangle in frequency is a special case. And if beta is equal to 1, it just falls off from the beginning. So beta determines for how long you're flat before you start to run off, essentially. Okay, so these are the pulses for 3 different values of beta. And then in the time domain, they look like this. Okay? So they have actually pretty significant side lobe, as you can see. So you may wonder, how come these guys don't have ISI, right? So imagine I take this guy, and then I put another one shifted by t, right? You think they're going to be ISI free? Or I mean, they are, right? But do you doubt it? It's hard for you to see it, why they don't have ISI. Okay, so look at this, right? On every multiple of t, they cross 0. You see? That's the key, right? So even though it has non-zero values, when it comes to the point of sampling, when you're going to sample the signal, remember here, right? Every time you're going to sample here, every capital T, you're going to run into one of these zeros. So only here you're going to actually pick the signal, but then on all the other multiples of t, you're going to always pick a 0. So as soon as you have a shifted version of this, as long as you stay within the capital T sampling points, you have just a 0. So let me try to help you out with the picture. So this is pretty important stuff. It's non-trivial. Okay, so we have okay, forgive my horrible handwriting and drawing, but this is an attempt to reproduce that same picture. Okay, so that's the symbol. Now, after capital T seconds, which is here, I'm sending another one. Okay, so I'm going to draw it in dashed to distinguish it, right? So I'm going to send another symbol. here. Okay. So hopefully you get the idea, right? It's the same, it's supposed to be the exact same shape, but shifted by one symbol time. And it has a different information. It could actually be a minus, it could be flipped over if the bit is, depending on the bit, it could have a different phase or sign. For example, if it's BPSK, it could be 1 or -1. But shape-wise, it's the same shape, just displays capital T. But you see the zero crossings are lined up precisely, right? So if I sample at this point in time, I'm getting this guy information, but this guy is giving me 0. You see? So they're not mixing. I'm not mixing them up. I'm just picking up this guy. Now, in the next symbol time, I'm just picking up this guy. The other one is actually giving 0 here. So they don't interfere with each other, right? And there's going to be another one. In fact, there's an infinite number of these guys lined up. Every t seconds, there's a new one coming. But at each sampling point, only one of them is non-zero. All the other ones are 0, guaranteed to be 0 by design. Okay? So even though they're all seemingly mixed up, at the sampling instance, when we make our decisions, we just pick one of them. So every time we sample here, we just pick one and only one of the symbols. Okay? Yes? Yes. Yes, very good point. I mean, very good concern.
How does that affect the frequency?
Yeah, very good concern. Okay, so this is a really good question, right? The question is, these shapes are infinitely long in time, right? At least in theory. These tails go on forever. Ever so smaller, they go on forever. So how is this done in practice, right? I mean, one can wonder, how can you do this in practice? So how can you send something before it starts? So what you do is, first of all, there are two, the answer has two parts. First, you actually truncate this. So even though these tails go on forever, they get truncated. Okay? So usually the symbols are synthesized to have a duration of about 60s, I would say. So usually you just cut it off around -5, -6 on each side. Okay? That's the first part of the answer. Now, so the second part is what happens with the negative, with the anti-causal part. So let me deny that for a second. Let's complete the first part of the answer. So you truncate it in the time domain. What does that do to the frequency domain? So it actually reshapes it a little bit. Essentially, an easy way of truncating it something is to window it, right? So if you want to truncate a signal that is infinite, you can just multiply by a rectangle, right? By a window, and that way you can truncate it, right? So that means you convolve its frequency pulse, frequency shape with something else. So actually, that creates some ripples. So what happens is that this very nice shape that goes on to 0 and then stays 0 forever, when you actually window it in the time domain to make it finite, it causes some lobes over here. So there is some spectrum regrowth, it's called. So this becomes non-zero for some frequencies over here. But it's pretty weak. So as long as you're careful with the windowing, these lobes are pretty binary. So it's a small effect, but it does break this perfectly nice shape in the frequency domain. Now, the second part of the answer of the question is, well, even if you window these guys so that they're now finite, right? Some of it comes in 4 times 0. So what you do is you just deny everything, right? So instead of calling this time 0, call this time 4t, and call this 0. Right? You just deny everything for 4t, so that this is 0 now, this is 4t, and this is 8t. Okay, so now everything is causal, and nothing starts before 0 in some way. So you do a combination of techniques. You deny everything by a few symbol clocks, symbol times, to make it causal, and then you window it to make it finite. So that's how it's actually done. Okay, and the windowing that's used actually, so you don't just truncate this. You actually multiply it by a smooth window to just progressively cut it off as opposed to abruptly. So you want to make everything smooth always. Otherwise, the frequency shape gets very distorted. Yes?
You need to use a higher beta, and then that would do.
Yes, very good point, actually. What's the role of beta, right? What's the importance of beta?
Well,
Okay.
it's sharpness of your.
Yes, exactly. So the smaller the beta, the more compact in frequency, right? So one can ask the question, why wouldn't you use the smallest possible beta, right? For example, I told you that in GSM they use 0.35, right? So you can ask, well, why wouldn't you use 0 or 0.1, right? That's a very valid question. So let's look at the answer, right? As always happens in Fourier transformation is duality, right? Let's go to the other domain, time domain. What happens when beta is smaller? Yes, you have a larger cycle, exactly. So what's the consequence of this? We said that the crossing points are 0, right? And that remains true. For any beta, you always have 0 in the multiples of t, you have a 0, right? But the cycles in between grow larger, right? Why is that a problem? Why can that be a problem? Anybody else? Okay, imagine your synchronization is not perfect, right? So your sampling point is displaced a little bit. Then it becomes important, right? So imagine that my sampling is, instead of at 2t and 3t and 4t, is 10% off, for example, right? So it's at 2.1t, 3.1t. Then the larger the beta, sorry, the smaller the beta, the larger the ISI I'm going to pick up, right? So there is a trade-off between robustness to synchronization inaccuracies and frequency compactness. And so this has to be carefully studied, right? So to save more bandwidth, you have to make your synchronization more precise. So 35%, which is what they use in GSM, is a pretty good trade-off. So it's fairly small, it's close to 0, but it has a little bit of tolerance in case that your sampling points are off, which are always going to be off by a little bit. So you want to make sure that if you have a 10% error in the sampling point, you don't pick up a lot of ISI, right? So that's a trade-off with beta. Excellent point. Okay, that's about it. Let me see. Yeah, that is it. Questions here, besides these very good ones that have been made already? Anybody? Okay, so I think this is a good time for the break. Let's relax, and we'll pick it up in 15 minutes, okay? Okay. Let's go for the second half. So we completed chapter 5, and we'll start with chapter 6. There's a new set of slides that was posted by Eftigios a few days ago. So hopefully some of you guys had a chance to download it. Okay, so let's quickly review the key ideas we learned in chapter 5, because chapter 6 is a complete direct continuation of chapter 5. I think it was just one chapter and she broke it up in two because it was too long. So we learned that modulation allows us to map bits onto a signal for transmission. Remember, there are two main classes of modulation, linear and nonlinear, and there are trade-offs here involving spectrum efficiency versus power efficiency. So we talked about that, and we made the point that nowadays there's a clear trend to go towards linear modulations only. And so far we studied modulation for unfaded channels with additive white Gaussian noise, assuming ideal synchronization in time, frequency, and when pertinent, also in phase. Okay? And modulations are defined in low-pass notation by a constellation of points on the IQ plane, and sometimes just on the I line, if we use PAM. When the points are equiprobable, and for us they're always going to be, optimum detection boils down to this maximum magnitude criterion, which in turn boils down to minimum distances. In fact, with Gaussian noise, this M1 criterion is tantamount to minimum Euclidean distances on the IQ plane. We saw that the exact computation of error probabilities requires, in general, a numerical integration. So then we use the union bound to find simple and convenient expressions via the Q function. And for high scenario, we can express the Q function using this exponential approximation. So we get something in closed form. We saw the importance of gray mapping in terms of minimizing the number of bit errors when a symbol is in error. And we described the three main classes of linear modulations: PAM, PSK, and QAM. The simplest subclass of QAM are the ones that are square, although better constellations can be obtained with careful shaping. The best performance is obtained with coherent detection, which requires recovering the phase of the signal, the phase of the oscillator, to be precise. So we saw that one can also use non-coherent detection, which does away with this requirement, but at the expense of some performance degradation. And finally, we saw how to shape our signals, our symbols, using pole shaping, carefully designed to minimize bandwidth consumption without causing ISI. Okay, so to achieve this, we have to satisfy the Nyquist criterion. And we saw that raised cosine pulses are a good solution, and in fact, is the solution that is used by every commercial system. So let's start with the stuff in chapter 6. So far, we have described modulations in AWGN channels. And we're now going to proceed to specialize the error probability for each of the modulations, PAM, QAM, and PSK. And we'll study the impact on the performance of flat fading, frequency selective fading, which means delay spread, remember, and then ISI won't be inevitable, and also of Doppler spread. Okay, so for the remaining of this chapter, we're still going to assume perfect carrier synchronization, perfect timing recovery, and in the case of coherent modulation, also perfect coherent reception. Okay, so perfect phase alignment between transmitter and receiver. So let's revisit some basic notions first. If the passband noise power spectral density is N0 over 2, the SNR is the received power P sub r divided by the noise power, which is N sub 0 times B. Okay, so N sub 0 is watts per hertz, and B is hertz, so this is watts. Okay, so if PR is a received signal, the energy of its symbol is PR times Ts. Okay, so we have a power of PR, and the duration in time is Ts. So the product gives us the energy of the symbol. ES. We'll use ES to denote the energy per symbol. Okay, so making a substitution up here, we can express the SNR as ES divided by N sub 0 times B times Ts. All right? So we're going to denote the ratio ES over N0 by gamma S. Okay, and so gamma S, just rearranging this term, we can see that gamma S is equal to SNR times B times TS. And we saw when studying chapter 3 that TS is roughly 1 over B. Okay, so the symbol time is roughly the reciprocal of the signal bandwidth. So we have that gamma S is roughly equal to the SNR. Okay, so we're going to take these to be in a quantity. And so we're going to use SNR and gamma S as equivalent terms, and also ES over N0. Okay, so we're going to have that all these terms are going to be equivalent for us. So we have that SNR equal to gamma S equal to energy per symbol over N sub 0. Okay, so gamma H is convenient because it's very compact. Then we have something that's the energy per bit, EB, which is ES divided by the number of bits per symbol. So we have k bits per symbol, and k is log 2 of m. Okay, so the energy per bit is the energy per symbol divided by log 2 of m. So m is the number of points in the constellation. All right, so the ratio EB over N0 will be denoted by gamma B. So both these quantities, gamma S and gamma B, are different, but they're both very important. So we're going to be using both of them. And they relate as, so we have gamma S and gamma B, and they relate as gamma B equals gamma S divided log 2 of m, where m is the number of points in the constellation.
So gamma B is the signal noise ratio.
Yeah, gamma B is the SNR per bit, exactly. So in fact, often it's called that way. So gamma S is the SNR per symbol, and gamma B is the SNR per bit, exactly. Good point. Now, we also have, remember, the probability of error per symbol, PE, and the one per bit, PB. Now, under gray mapping, and neglecting the probability that you can have errors that are not between neighbors, we had that PB is approximately equal to PE divided by log 2 of m. Okay, and this is an approximation because, first of all, it's only true if we had gray mapping, and second, it's only true if all the errors are always between neighbors. Okay, so sometimes you may have errors between symbols, points that are not neighbors. If you have really bad noise, you may get pushed really far away. But neglecting that chance as small, PB is about PE divided by log 2 of m, and that's pretty close. Okay, so let's keep these notions in handy because we'll be using all of them. So let's start by studying the simplest possible constellation, which is BPSK. Okay, so this constellation just has 2 points, so it doesn't get any smaller than that. So we have 1 point here and 1 point here. Okay, this is called BPSK for binary PSK. So it has 2 faces, 0 or pi. And notice that BPSK, which is 2 PSK, right, is also equal to 2 PAM. Okay, so these constellations actually coincide, right? 2 points in amplitude over the line correspond to 2 points in a circle exactly over here on the line also. So 2 PAM and 2 PSK are the same, and they're usually called BPSK. And this is the simplest possible constellation. So as we already mentioned in the previous lecture, for the previous chapter, for BPSK, the union bound is exact. And this is the expression. Okay? The double summation just disappears because there's only 2 points. So we end up with just a Q function of d min, which is just the distance between these 2 points, divided by root of 2 and 0. Okay? Now, in this case, the energy per symbol and the energy per bit are the same, And gamma B and gamma S are the same because there is only 2 points. So the log 2 of 2 is equal to 1. So what's the energy per symbol? Well, if this point is A, and this point is minus A, right? So the energy is A squared, clearly. So the energy per symbol is A squared, and the energy per bit is also A squared. And the mean is 2A, right? You agree with me that between these 2 points, the distance is A minus minus A is equal to 2A. So we can relate the mean with 2A, and then we can relate the mean with A, and then we can relate A with ES or EB, right? So capital H has the square root of EB, and d mean is 2A, right? So you agree with me that d mean in this case is equal to twice A, and A is square root of EB, right? So d mean is twice the square root of EB, okay? We divide by square root of 2 and 0 over here, and we have some square root of 2 cancellation, and we get Q of root of 2 gamma B. All right, everybody agrees? So using these expressions, these relationships, we can get from this Q function to this Q function. And notice that PE and PB are also equal here, because log 2 of 2 is equal to 1. So everything is very easy, right, in BPSK. That's why, I mean, it's so simple. So that's it, right? We have both probabilities of error as function of gamma B. And since gamma B is equal to gamma S, we can relate all the probabilities to all the gammas. All right? So piece of cake. Any questions here for BPSK? Are you guys all comfortable with this? Okay. I'll take that to be a yes. Okay. So let's go to QPSK, which is the next constellation in complexity, and by far the most commonly used in the real world. So QPSK has 4 points. So we have these 2 points, and now we have this guy here and this guy here. Okay, so this is J times A. This is minus J times A. Okay, we have 4 points in a circle, size capital A, amplitude. And we can use the union bound to express the P sub B using this summation of Q functions. Okay, so I've just applied the formula for the union bound that you guys already know. We get this summation of 3 different Q functions, depending on the distances between the different points. Okay, and actually, we did this as an example last week, so you guys have seen this before. We did this exact case of QPSK. Now, in this case, let's see what happens with the energies, right? The energy per symbol is twice the energy per bit, because there are 2 bits here, right? We have 4 points, and log 2 of 2 is 2, so we have 2 bits. So ES equals twice EB, right? And then ES equals A squared, right? Because this is a circle, so all the points have the same amplitude A. So we have this double relationship. Now, how about the distances? Well, between 1 and 3, let's take them to be 1 here and 3 here. Distance is 2A, as before. Between 1 and 2 is square root of 2 times A. And between 1 and 3 is also square root of 2 times A. Okay, so this is what we have here. 2A and then root of 2 times A. So the union bound, again, we saw this as an example last week. Union bound for QPSK gives us this sum of Q functions. Now let's look at the nearest neighbor approximation. So we have d min is root of 2 times A, and we have 2 neighbors per point, right? So each of these guys has 2 minimum distance neighbors. So we get twice the Q function of square root of gamma s, which is pretty close, right? So here we got these first parts right, and then we just didn't get the second part, but this is pretty minor. So it's a pretty good approximation as usual. Now, as it turns out, we can actually get the exact, so remember these are all bounds, right, in general, the union bound and all these approximations are just approximations of bounds. Now, for QPSK also, as in PPSK, we can get the exact expressions for PE without integrating. And the key to doing this, the trick is to exploit the intimate relationship between BPSK and QPSK. So even though apparently for QPSK we had to integrate to get the exact PE, we can express QPSK as the product of two BPSKs, orthogonal. Okay, so we can take this to be a BPSK on the I-axis and a BPSK on the Q-axis. Independent BPSKs in quadrature. And since we just solved for BPSK the exact PE we're here, we can actually work this out and get an exact expression also for QPSK. So let's do this. We'll interpret QPSK as two independent BPSKs in quadrature. So for each of the two BPSKs, we have this formula which is derived, right? Q of root of 2 gamma b. Now, how do we go from BPSK to the QPSK here? So let's do it. Okay, so the probability that we have an error, PE, is equal to 1 minus the probability that we have no error. So let's call this PE bar. So bar usually is used to denote negation. So this is just the negative, right? So PE is equal to 1 minus P bar, where PE bar is the probability that there is no error in the QPSK. Okay? Now, let me express this. Okay, so in order to have no error in the QPSK, what do we need to have on the two BPSKs that compose it? Right? We need to have simultaneously what? Can we have an error in one of them? No, we have to have no errors in both of them, right? So we need to have no errors in I and no errors in Q. Now, we just said that these are independent, right? So we can multiply out the probabilities, right? Remember that when you have the probability of two events happening, if they're independent, you can just multiply them out. So the probability that there is no error in the QPSK is equal to a probability that there is no error in the I branch times probability that there is no error in the Q branch. Okay, something like this. So we have a product of no error probabilities on the I and on the Q BPSKs. Okay, now this is equal to 1 minus oops, sorry. Okay, so the probability that there is no error in I is 1 minus the probability that there is error in I. Probability that there is no error in Q is 1 minus the probability that there is error in Q. All right, so we're almost done now. Now, I and Q are identical, right? Each one is a BPSK, independent, but in terms of probabilities, they're identical, right? They have the same distance between the points, right? Except for the fact that one is in I and one is in Q, they're indistinguishable, right? So this is the same as 1 minus the probability of error of a BPSK, I or Q, squared, right? So I'm just taking these guys to be equal, so it's one of them squared. And we're done, right? This is what we have here. So I just show you how to get this expression. And now we know that this expression here is just a Q function, right? So it's this guy comes over here because it's for the BPSK. And we're done, right? Now we can just expand this square. So we get 1 plus a Q squared minus the cross product times 2, so we get twice the q. So the 1 cancels out with this 1 over here, and we get twice the q of root of 2 gamma b minus q squared of root of 2 gamma b. And remember that in this case, 2 gamma b is equal to gamma s. So we get twice the q of root of gamma s minus q squared of root of gamma s. And this is exact for QPSKs, right? So using this trick of decomposing it in BPSKs, we actually can solve it in exact form. Now let's compare this with the different bounds we had. So for the union bound, we had this, okay? So the first term is correct. It's twice the q of root of gamma s. And here we have plus q of root of 2 gamma s. So this first part was right. But here, instead of having a negative as we should have, we had a positive, right? These are small terms, right? Q squared is very small. And this is q of twice the argument. So it's also small. But it has a wrong sign. So it's a correction in the wrong direction, right? Instead, the nearest neighbor gave us just this leading term. So it had no correction, right? So this one is a little better, right? Because we didn't have this negative, but at least we didn't have a positive. So it's a little better. So the nearest neighbor is actually a little better than the union bound here. Although the difference is small, but it is a little better. Yes?
So you're saying that they're independent, the two, but they're really not. Because the nearest neighbor is telling us that if there's an error, it's going to go to the nearest neighbor. It's not going to go to up from negative AJ to JA. It's going to go to probably negative A or A, right?
Right, so you're saying, okay, this point over here, for example, will probably end up being mapped to the other BPSK. Yeah, that's correct, but I used independence only in one step, right? Which is here. So I used independence to express the fact that the probability that there is error in the QPSK is the product of the probabilities, right? So, and what I use is correct. So the probability that there is an error in either of them is independent. In other words, the probability that this bit is in error does not depend on this other bit. But the final destination of the error is actually also independent, but it could actually go to the other BPSK, is what you're saying. So what you're saying is correct, but it doesn't challenge the fact that the chances that each of the two bits is in error are the same because the noise has the same properties in both directions, right? So this is true because the noise is Gaussian, right? Imagine I give you a noise that doesn't have this property. For example, imagine I give you a noise that is stronger in phase than in quadrature, right? Then this wouldn't be true anymore, right? So I need the noise to be symmetric in all possible ways. And Gaussian noise is, but it could not be, it could be not so, right? For example, if you had impulse noise that doesn't have, only has in-phase component, for example, but this would not be true, right? So it is not universal, but it is true for our case. Now you're correct in that most of the time, when you do make a mistake, you're going to end up going to the point that is in the other BPSK, right? But it doesn't invalidate the derivation. Other questions? All right. So let's see a quick example. Say we have QPSK with gamma b equal to 7 dB, which in linear scale is equal to 5, which is over 5. Then we can just plug this into the Q function, and we get that PB is equal to 7.7 times 10 to the minus 4. Now, the exact error probability using this formula we just found is 1.5 times 10 to the minus 3, right? Now, let's use the approximation that PB is equal to P is about P divided by 2. We'll get something that is actually very close, okay? So this validates this approximation, this gray map. So this gray mapping approximation in this case is validated. And nearest neighbor tells us that this is 1.545. So down to the third decimal point, they're identical. So as you can see, the wrong of this Q square here is really small. So it doesn't show off in the first 3 decimal points, okay? So in this case, all of the expressions are very close because they all have in common the dominant part, which is this 2q of root of gamma s. So the details are in the second order terms, which turn out to be very small in this case. Okay, yes?
Does approximation usually work when the constellation is symmetric? Because when it's not, the minimum distance only is shared by a few points.
You're asking about the nearest neighbor or approximation, or?
Yeah, exactly.
Yeah, so the question is, what happens when, with the nearest neighbor, when the constellation is not symmetric, right? For example, you may have cases where the number of points at minimum distance is not the same for every point, right? Is that what you have in mind, or?
Exactly.
Right? For example, and a typical case, so this is a good question. A typical case is QPS 16 QAM, right? So you have something like this. So a guy like this point, for example, has 4 neighbors at the minimum distance, whereas the guy at the corner only has 2, right? So there's 2 ways to compute it in this case. You can compute the neighbor approximation for every point of the 16 and average this out. That's one way, which is the best way. Or you can just take the worst case, which is the guy with the most neighbors. So in this case, you get something that's more conservative. So it's not going to be so close. So the best way is to do it 16 times, 1 for each point, and then you average the 16 values. And that's the way I recommend. And the other way is just to use the worst case, which is use the maximum number of neighbors. In this case, you would be using 4. Right? I don't know if that's exactly the question you had in mind. Or... Okay. And in fact, I think that this came up, as Shruti reminded me, in one of the homework problems, right? So either way you did it is fine. But the better answer is going to be obtained if you average out the values for the different, for each of the points. Right? But if you did it the other way, it's also okay. The textbook is a bit fuzzy about it. So, and the reason it's fuzzy is because both ways are used. So she says you can average it if you want to, but you don't have to, because it can be done in both ways. Okay, so we saw BPSK and QPSK. Now how about MPSK with more than M being bigger than 4? Say 8 PSK, for example, or 16 or whatever. Well, in this case, the dmin has this formula. Remember we saw this before. Is 2a sine of pi divided by m. And the energy per symbol is a squared. Nearest neighbor is easy to compute because each point in a circle has 2 neighbors, exactly. So in this case, there's no problem, right? Everything is symmetric in the PS case. So we have this nearest neighbor is twice q of dmin over root of 2 and 0. And we can put this as function of gamma s, right? By converting dmin into, okay, so we can take dmin and replace it by this formula over here. And then we can replace a by square root of square root of es, and then combine es and n sub 0 into gamma s. And if you do that, you can get this expression on the right. So it's twice the q of root of 2 gamma s times sine of pi divided by m. Okay? So this one is as function of gamma s and capital M. And in this case, the exact error probability cannot be obtained except by integrating. All right, so we can expand this integral into an integral that looks nicer, but still pretty nasty. So if you want to get the exact values for the PE, you have to solve this integration, which can be done using Mathematica or MATLAB if one wants to, but it cannot be done in closed form. Okay, so here we have to use the bounds and the approximations. And that's all I'm going to say about here, about PSK. Questions? Okay, so that's it about PSK. We saw BPSK, QPSK, and then general MPSK. And now we'll look at PAM very quickly. Remember that the simplest case, which is 2 PAM, equals BPSK. So we already saw that case. So let's say that we have MPAM with the M bigger than 2. So dmin is twice d, which is so 2d is the spacing between points on a line. Remember, these are points on a line, spaced by 2d. We have this formula for the energy per symbol, which is 1/3 of m squared minus 1 times d squared. And in this case, also we can compute P exactly without integration. We can exploit the simplicity of this constellation. So we have these points on a line. Okay, I'm just going to draw 4 points, but they can be, any number of even number of points. Actually, let me draw 6. Make the point better. So one can easily see that there are 2 classes of points here. There are the guys on the extremes, and then everybody else, right? Why the difference? Well, any guy in the middle has 2 neighbors, one on the right, one on the left. But the 2 guys on the extremes only have 1 neighbor, right? Because there's nobody else this way or that way. So we have these 2 classes of points. We have to treat them differently. For the m-2 inner points, we have an error if the noise exceeds d. Remember that the spacing between 2 points is 2d, right? So this is right. So if the noise is bigger than d, we're going to be pushed into the vicinity of the other point, and we'll make a mistake, right? So that will happen if with probability q of d divided by root of n0 divided by 2. Okay. Now, because there are 2 neighbors, one on the right, one on the left, we have a factor of 2 in front. Okay. So that's the probability of an error for the inner points. Now, for the outer points, there are 2 outer points. The error occurs if the noise exceeds d in only one direction, right? In this case, for example, if the noise is bigger than d in the negative direction, we're going to get pushed over into this guy's neighborhood, and we'll make a mistake. But on this direction, there's no problem, right? Even if the noise is huge and puts us over here, still, the closest point is still the correct one. So there is no problem here. The noise can push us to the right as much as we want. We don't care. To the left is when we can make a mistake, because there's a neighbor there. So in this case, we have the same Q, but only once, as opposed to twice. So now we just put these 2 numbers together, and we say, okay, for the m-2 points on the inner points, m-2 over m points, we have twice this Q. And for the outer points, 2 out of m, we have the single Q. And it's the same Q in both cases, right? So you can just take it out and then rearrange these 2 terms with a little bit of algebra. And we get twice m-1 divided by m times Q. That's the probability of error. Now, using this equation over here, what is it? Oh, okay. Here we can relate d squared with E sub s, right? So we have d here. We can unravel these and say, okay, so ES equals 1/3 m squared minus 1 divided by 2. So we have that d squared is equal to 3 times ES divided by m squared minus 1, right? And we want to have d, not d squared. So we take the square root of this. We say, okay, so d is equal to this. And then divided by n0 over 2 root. Okay, we have this guy. And remember, ES over n0 is gamma s. So we can just boom these 2 square roots together and just rearrange the terms. And we get square root of 6 gamma s over m squared minus 1. Okay? You can see that these 2 is going to come on top, and times 3 is going to give us a 6. ES over n0 is going to give us gamma s, and then we have m squared minus 1 in the bottom, at the bottom. Okay? So that's the final answer. And this is an exact expression again. So as in BPSK and QPSK, for PAM, we can also get the exact expression. And if we apply the nearest neighbor, we're actually going to find the same answer. So in this case, the nearest neighbor approximation is also exact. And yeah, that's it on PAM. Questions? Okay, very good. Okay, so the final chapter of this part is, of course, QAM. And okay, for general QAMs, there is no solution other than the integration. Okay, for arbitrary QAMs, you have to do the integral numerically. That's it. Now, for square QAMs, we can use the same trick that we just used for BPSK. So we can express a square QAM as the product of two orthogonal PAMs. Okay? So if you have an MQAM, we can express it as the product of two orthogonal PAMs with square root of m points, right? So square root of m times square root of m is going to give us m. For example, a 16 QAM is the product of two 4 PAMs. Okay? Each will have the power. Remember, the power has to be divided by half, right? So half the power goes on the in phase, half on the quadrature. So for each of these, decomposed constellations, PAMs, I and Q, the P sub B is the one we just derived for PAM, right? Here it is. So this formula that we derived for PAM, which is exact, now it's on each of the two branches, I and Q. Okay, so we just put it up here again. It's the same formula, except that I replaced m with square root of m. Okay, remember that we have m points on the QAM, so we have root of m on each of the PAMs. So for each of the branches, P sub B is this formula, where I just replaced m by root of m, and I divided by 2 the gamma sub s. Why? Because half the power goes into I and half the power goes into Q. Okay? So the corresponding gamma, the gamma of the fictitious PAM on each of the branches has only half the power of the total power that we have. Okay? So with these two corrections, we get this formula for the I and the Q branches. Now, as we saw before, an error occurs when either of them is in error. So we can use the same trick, right? We write PE equals 1 minus PE bar, okay? And now express this P bar as the product of the P bars on both branches. So and now so we use the same technique that we use for BPSK conversion to QPSK. And since the I and Q are independent but statistically equivalent, we get this guy squared over here. Okay, so it's exactly the same procedure, except that instead of having a Q function, we have this somewhat more complicated expression. And that's it, right? So this is for the square QAM, this is the exact error probability. And we can compare it against the different bounds and approximations, which in this case are not exact. So the nearest neighbor in this case is not exact. And it's less, so you can use this exact formula to calibrate the accuracy of the nearest neighbor approximation. If the QAM is not square, as I said, the decomposition into orthogonal PAMs is not upheld. And so, bless you, we do not have an exact expression. Okay, in that case, we have to use nearest neighbor and union bounds. All right? So with that, we're done with QAM. Questions? Okay, so by now, you guys probably have noticed a certain pattern here in all these formulas, right? All of these exact or approximate expressions that we have found for PE all have the form of something times some Q function of something else, right? If we go back and look at each of them, they all have this form. It's some coefficient alpha, which depends on the type of constellation, so I'm calling it gamma m, alpha m, times the Q function of some other coefficient, beta, which also depends on the constellation, beta m, times gamma s, right? So these alphas and betas are tabulated for your convenience in table 6.1, which I shall look to put up. Okay, yeah, this is it. Okay, so some of these constellations we have not seen, so don't worry about those. But for the ones we have seen, here you can find these alphas and betas to express these probabilities using Q function, using this form, right? So we're saying, okay, which are the alphas and betas, so we can build a formula of this form for each constellation. So here we have BPSK. Okay, remember that in this case we have an exact formula, so that's why it's inequality. It's Q of root of 2 times gamma B. So in this case, the alpha is 1 and beta is square root of 2. For QPSK, we had these expressions here. So alpha is 2, here alpha is 1. So in this column, we have P, okay, a point for notation, right? Professor Goldsmith uses sometimes P sub B, sometimes P sub S. They both mean the same. It's the error probability per symbol. And they use P sub B, okay? I think in chapter 5, she calls it P sub B. In chapter 6, P sub S, then back to P sub B. So I'm just using P sub B, okay? But P sub P and P sub S in the textbook are the same. So I hope that won't get you confused. So these columns are for P sub S. And you can build similar formulas for P sub B, of course, with different coefficients in some cases. So we have BPSK in this row, QPSK in this row. We have PAM in this row, PSK, and rectangular QAM. Okay, and even formulas for non-rectangular QAM, which are approximate, and which we have not seen. Okay, so in every case, what's before the Q is the alpha coefficient. What's inside the Q, except for the gamma, is the beta coefficient. So for the first column, we have this, in that table, we have this P sub B or P sub S as function of gamma S. And you can use similar equations for P sub B as function of gamma B. All right, so that table is very useful. So you can quickly find what you need. Okay, so we're done here. And we'll move on to differential PSK now. Before that, questions? Okay, so let's talk quickly about differential PSK. In this case, differential PSK, remember here the information is in the phase difference. The exact expression for P sub B requires a complicated numerical integration, which we won't get into. And what's worse, our usual approximations do not apply. So union bounds and nearest neighbor, those don't work for differential. So as we saw, to evaluate the difference in phases between consecutive symbols, we need to subtract the phases from one another. So we can just, remember, conjugate one of them and then multiply them out. That gives us a difference in the phases. Now, when we subtract two terms that have independent noises, what happens is that the noises are going to add up. So since the noises are independent, they're going to compound and accumulate. So the subtraction process that we need to perform to compute the phase difference essentially is going to double our noise. Okay? So as a result, the performance of differential PSK is roughly 3 dB worse than coherent PSK. 3 dB worse because we have about twice as much noise as a result of this subtraction. So the gamma is reduced by about half. So we get the 3 dB performance degradation. It's an approximation, but it's pretty close. Okay? So the price to pay for having differential detection, which is simpler, is to lose about 3 dB in performance. Now, there's only one case, which is differential BPSK. for which a simple exact expression can be found for the PE and PB, which is here at the bottom of the slide. So it's 1/2 of e to the minus gamma s. So it's a very nice formula, but it only works for differential BPSK when you have only 2 points, only 2 different phases, 2 different phase changes between symbols, either 0 or pi. So in that case, we have this very useful formula. Otherwise, we have just very nasty integrals. So mostly when it comes to BPSK, mostly we'll talk about only differential BPSK. Okay, so we're going to start with fading now. So far we had unfaded channels. Now we're going to start with PE in fading channels. So before that, questions about PE in no fading? Okay, so I know that there's a lot of formulas here that I've thrown at you guys. So between the homework we saw last week and the new homework, hopefully you get to familiarize yourself with these formulas and play with them a little bit. And sort of, know where to find them when you need them, essentially. Yes?
Differential error probability in differential PSK. So this is only gamma as PBSK. Well, we only have our equation for when it's good.
Yeah, we only have this formula for differential BPSK, right? So for the other ones, there's no easy formulas, unfortunately. Yeah, so we have to do it numerically. It's pretty complicated. So by and large, in terms of differential, we're going to restrict ourselves to differential BPSK. We're not going to be using more complicated forms of BPSK because there are no formulas really. So there's nothing I can ask from you guys that involves integrations. So mostly we'll be just, when it comes to differential, mostly we're going to be just dealing with differential BPSK. Okay, so let's throw some fading on top of it and see what happens. In the absence of fading, we saw that PE depends only on gamma. Okay, gamma S, gamma B, so it depends only on the SNR. Now, what happens when we have fading? Well, the received signal power varies randomly over time, and so gamma is now going to be a random variable. Okay, so since gamma is a random variable, P sub B and P sub B, which are functions of gamma, are also going to be random variables. Okay, so these error probabilities themselves are going to be random. So this looks pretty tough, eh? We're going to be invoking different performance measures depending on the type of fading. So in particular, depending on whether the fading is slow or fast. And remember here that, I think I told you guys a bit about this in chapter 3. The fading classification depends on how the coherence time of the fading relates to coding block length. Now, we've not seen coding yet. We'll start with next week or the week after with coding. But so for now, our coding block length is just one symbol. So we're going to be doing, since there's no coding, it's symbol by symbol. Okay? So fast fading or slow fading is going to depend on whether the coherence time of the channel is longer or shorter than the symbol time T sub S. Okay? So how a coherence time relates to T sub S is going to tell us if the fading is slow or fast. Remember, coherence time is the time it takes for the channel to change significantly over time. Okay? And it's roughly the reciprocal of the Doppler spread. Okay? Remember we saw that in chapter 3. But we're going to revisit these concepts now. So in slow fading channels, the appropriate metrics are the outage probabilities. Okay? So we studied this extensively, remember, for in chapters 2 and 4. 2 for shallow fadings, right? And 4 also for the capacities, right? So remember that the outage probability, P out, is the probability that the received power is below some minimum acceptable level. Okay? So equivalently, the probability that gamma S is below some minimum. Okay? So outages cause long bursts of errors, which are problematic. Now, in fast fading channels, when the channel changes very fast, a more appropriate measure is the average error probability. Okay? Because in this case, the phases are so short that fading causes sporadic and dispersed errors. So in this case, a better measure is just the average. In this case, it's the average. And sometimes you want to combine both metrics into one. And an easy reason why we want to do that is to account for both slow fading and and fast fading, right? Imagine we have, in fact, don't imagine, we always have, in reality, a combination of shadow fading, which is slow, and multiple fading, which is relatively fast. Remember that shadow fading changes on scales of meters or tens of meters, and fast fading changes on the scales of centimeters or inches. So these changes in terms of time on the order of seconds or even minutes, and fast fading on the order of milliseconds. Okay, so when we have both types of fading, often we want to combine the notion of outage with the notion of an average. Okay, so we'll see how to do that. It's actually easier than it sounds. So let's start with outages. Okay, so let's assume we have only slow fading, for example, only outage, only log normal shadow fading. Okay, so let's denote by gamma 0 the minimum acceptable value for gamma. And here, a big note of caution. So I'm using the notation that's in the textbook. I'm going to use gamma 0. But remember, we use gamma 0 in chapter 4 to refer to the threshold for water filling. Remember? That's a different gamma 0. Okay? So these are two different quantities that are called gamma 0 because we're just short of Greek variables, I guess. But they're different. So be careful because some of you guys got confused in the midterm first problem between the gammas of the exponents of the path laws and the gammas of the SNRs. Okay, so it's a shame. So be careful. There's a lot of gammas here in this book. And to be fair to Professor Goldsmith, these are the values that are used also in the community. So she's just respecting the notation people use. So gamma is used to both to use the exponent and to use the SNR, to denote the SNR. So by context, one knows which gamma is which gamma now. So watch out. Okay, so this gamma 0 here is the minimum acceptable value for gamma. Okay, so the outage probability is the probability that gamma s is below gamma 0. And how do we find it? Well, if we're given the PDF of gamma, we just integrate from 0 to gamma 0. Okay, so given the PDF, we just integrate over the range that we want, and we get the outage probability. Now, it so happens that the fading is Rayleigh, which is often the case, then remember that the distribution of gamma is exponential. And this is the PDF. It's a very nice, it's a very convenient formula because it's very simple. So in this case, we can just plug this formula in here and solve the integration and get something very compact, right? I don't think I have to solve this, but so we have to integrate between 0 and gamma 0. 1 over gamma S bar, which is the average of the fading, which it's a constant, so it comes outside, times e to the minus gamma over gamma S bar, integrated over gamma. Okay, so you can easily solve this integration, and you'll get 1 minus this exponential. So in this case, things look very nice and friendly, right? This is the outage probability as function of gamma 0 and gamma S bar. So gamma S bar is the average value of gamma S. So remember, what happens is that gamma S changes randomly over time, following a Rayleigh distribution. So the amplitude, to be precise, the amplitude of the signal follows a Rayleigh distribution. So the power of the signal follows the exponential distribution. And so gamma itself, gamma S, follows the exponential distribution. Okay, so it changes randomly over time, following an exponential distribution. And so gamma S bar is the average of the distribution. So the bigger the better, right? The bigger the average, the more power we're getting on average. And so the bigger gamma S bar, the smaller the outage. And on conversely, the bigger gamma 0, the bigger the outage. Because gamma 0 is the minimum that we want. So if we want a higher level, we're going to get more outages, right? So let me try a picture here. So if we look over time, gamma 0 is going to be varying over time. No, sorry, not gamma 0. Gamma S changes over time randomly. The PDF is exponential, okay? And the average, let's say, is here, okay? So this is the average. And around this average is randomly varying as we move around. And now we say, okay, I'm going to say that I have an outage when the actual value is below some gamma 0, which is down here. Okay, so that's gamma 0. And say, okay, how often is the signal with this distribution and this average below gamma 0? Well, in this case, it's here, right? Here, here, and here. Okay, so the total area of these events over this total area is the probability that it fell below this line, which is, should be pretty small. And we can find it exactly using this equation. Okay, so if we make the average of the signal higher, so we move this bar up, the whole signal is going to go up, and so chances of falling below gamma 0 are going to diminish, right? If we move it up, these values here are going to come up also. So eventually we're going to be better and better, and so P out is going to get better, so it's going to diminish, and so that's what happens if we increase gamma S. Now, if we increase gamma 0, things get worse, right? For example, if I put gamma 0 here, it's clear that I'm more often than before below gamma 0. Okay, so P out is going to increase. So you can easily see here the dependencies on gamma 0 and gamma S bar on the outage. Now we can invert this formula very easily and express gamma S bar as function of gamma 0 and P out. Okay, so we can just take a log on both sides, and we get that gamma S bar is bigger or equal. Okay, so what I'm doing here is I'm saying, okay, I want to make sure that P out is less or equal than 1 minus to the minus. Okay, so I made this into an inequality because even if I tell you I want P out to be 10%, if you give me 5%, I'm also happy, right? So as long as it's below a certain value, it's okay. So I made this into an inequality, and now I can just take a log on both sides and clear this out. And I get that gamma's, for this to be true, for this inequality to be true, I need that gamma S bar, the average of the fading, has to be larger than gamma 0 divided by minus the log of 1 minus P out. Now, we can take this in dB if we want. So when we have a ratio and we go into dB, we're going to have a difference, right? As we all know. That's the beauty of dB, right? So we find that gamma S bar in dB has to be bigger or equal than gamma 0 in dB plus something called the fading margin, the dB fade margin, which coming back here, as you can see, is essentially this denominator in dB, right? So there you go. It's minus 10 log 10 of minus log E of 1 minus P out. Okay, so that's the dB margin, which is over here. So let's go through an example. Say we have BPSK, okay? Slow rate of fading, so that the outage is the right metric to use. What is the required average gamma S such that 90% of the time, the error probability is smaller than 10 to the minus 4? So this is the type of question that we can now answer using these tools. So if we look at the formulas we saw in the previous part of the lecture for the the Q functions for the BPSK, formulas that you guys now have to use. Remember there was a Q of root of 2 gamma S, I think, or 2 gamma B, something like that for BPSK. So using that formula, we can show that to be at 10 to the minus 4 PE, we need gamma S to be 8.5 dB, okay, or gamma B. In this case, BPSK means that they're both the same. So to be at 10 to the minus 4, we need gamma S to be at least 8.5 dB or bigger, okay? So we have gamma S and gamma B, okay? So that's the minimum that we need, right? So that's going to become our gamma 0, all right? So we need this, and remember that gamma 0 was the minimum that we needed. So we're going to use this as gamma 0 over here. And now we have to compute this fade margin. So actually, you know what? I'm doing it in linear scale. So I'm not doing it in dB. So I'm using this formula here. So this is the linear version, and this is the dB version. And for the example, I'm using the linear version. Okay, so I don't want to confuse you. I'm using this version here. So I'm using gamma 0, which is 8.5 dB. So I convert it back into linear scale, and it's 10 to the power of 8.5 divided by 10. Okay, so I converted the 8.5 dB into linear scale. So that's here, gamma 0. And now I have to divide by minus log of 1 minus P out. So minus log of 1 minus P out. And I want a P out of 5%, right? I want to have 90% of the time this condition. So the outage is going to be 5%. So it's 1 minus 0.05. So I just work this out, plug it into the calculator, and I get 138.02, which in dB is 21.4. Okay, so what I found is that to have a probability of error of 10 to the minus 4, 90% of the time, with BPSK and no rarely fading, I need the gamma S bar to be 21.4 dB. So I know how much, so using this information, I can see how much power I have to transmit. Okay, so is this clear? Does the example help? Guys, don't be shy, eh? Is there any point unclear here? Okay, we'll see with the homework if it's true or not. So this is very reminiscent of what you guys were doing in chapter 2 for the shadow fading. Remember when you were doing cell coverages and cell outages and that kind of thing? So it's, the formulas are different, but it's a similar notion. Okay, so that's it for the outages. Okay, so the key is this one. This is the key formula, okay? And the equivalent in dB is this one. You can use either one. If you're more comfortable working in dB or in linear scale, either one. But the idea is that this formula couples the minimum requirement that you have, the outage that you can accept, and the average power, the average gamma that you need. Okay, so these are the three quantities that are coupled by this formula. And the gamma 0, the minimum threshold that you need, is typically determined by the type of constellation and the PE that you can accept. Okay, so these are all the pieces that fit together here. Now, let's say that we have, instead of slow fading, we have fast fading. Okay, and that's going to be the last topic for today. In this case, we want to compute averages as opposed to outages. So the average over the fading error probability is given by PE bar, and be careful here because I just realized I've been using earlier today PE bar to denote a negation. Okay, so bar, I was using it to denote a negation, which is actually pretty common, but it's also used to denote an average. Okay, so engineers tend to have these all these duplicities. So here it means average, okay? But luckily for you, I have also here the expectation. So the expected value of PE is just the integration from 0 to infinity of PE times the PDF of gamma. Okay, and now depending on the constellation, PE is going to be one of the formulas that we just found, right? One of these Q function formulas, depending on if it's BPSK, QPSK, QAM, etc. Each one has a different formula, right? So in rarely fading, the PDF of the fading is the usual exponential, which is I've been using for this last example. Okay, this familiar expression. So sometimes we can actually plug this in this integration, and if PE is sufficiently simple, we can actually solve this in closed form. For example, for BPSK in rarely fading, we have that PE is this Q function, remember? We just derived this like an hour ago. Is Q of root of 2 gamma. And the PDF of rarely fading is this exponential. Okay, over here. Just put it down here. So this is a tough integral. You have to integrate the Q function, but it can be solved in closed form. Takes a lot of work. And the answer is surprisingly simple. It says it's 1/2 times 1 minus square root of gamma s bar divided by 1 plus gamma s bar. Okay? So a very nice formula, surprisingly, given the nastiness of the integral. So this is the average PE or PB in fast Rayleigh fading with BPSK. Okay, and it's a function only of the average gamma s. So the average of the SNR. So average gamma s bar is the average SNR. Okay, so as function of the average SNR for BPSK in fast Rayleigh fading, we have directly here the error probability. Yes.
The PE for, well, the probability, the PE for Rayleigh's grading is equal to
Be careful.
oh, we're saying, oh, it's for
Right. So this formula is for BPSK, right? So if we had QPSK, we had found, I think it was twice the Q, right? It was 2Q. And then there's a correction term that we can neglect, which is a Q squared, something. So for QPSK, you can actually just put a factor of 2 outside, and you can get, essentially, it's the same thing times 2. And I'm not sure if inside of the Q there is a square root of 2 or not, but it's a similar formula, so you can also integrate it easily. In fact, most of the formulas look like something times Q of something, so you can use similar expression. And in fact, we'll see next week how to generalize it, but I think this is a good place to stop. So we'll stop here, and next week we'll see how to obtain more general formulas, and we'll finish the chapter. Okay? So thank you guys, and have a good week.